Thank you very much for staying for the final session. This is the graveyard shift. I think you'll agree with me that it's been a fantastic couple of days, some very interesting topics discussed. I've certainly learned a lot, and hopefully my presentation will dovetail quite well with one or two other presentations and show that we are all thinking along the same sort of lines and have the similar sort of problems to solve. I'm specifically going to talk about FLNG and its application in a harsh, hostile environment. Certain applications of technologies that have been discussed by others are by default not applicable, but what I will go through is standard design arguments from the point of view of the hull marine and the marine systems designer to the design of the floating facility. Okay, presentation, I'll do a brief slide on us, in case you don't know who we are. I'll then spend a little bit of time going through the key drivers that affect the sizing and configuration and fitting of the hull. That used to be called a barge. That now seems to be a substructure supporting the topsides. Then touch on some of the regulations that we have to apply, both international, national and company regulations, and then look at a group of considerations for different disciplines on different aspects of the barge, the hull design. Then move on to safety considerations, specifically to make sure we do produce an asset that is as safe as practically possible. And then a little bit of a diversion towards the end on what possible future technologies could be there and certain things that we'll probably have to look at in the exploitation of stranded gas fields, probably using FLNG technology in producing and getting the LNG to market. I don't know if any of you have heard very much about Babcock. Babcock is a company listed on the FTSE 100. 25,000 people, and it turns over about £4.5 billion sterling a year. So we're quite a large organisation. As that large organisations, we're a division of that organisation. We are ANMT, and that stands for Energy and Marine Technology. So basically we're in the marine business and the energy business. And within our division, there are approximately 900 to 1,000 engineers and designers, and obviously the support staff are among them. We are predominantly based in the UK, in sites on the south coast of England, northeast England, and in Scotland, but also have presence and offices in Singapore, Australia, New Zealand, and Canada. We've been involved in FPSO technology for nearly 25 years now. We were involved in the first conversions for the North Sea. It seems a very long time ago, and the technology seems vastly different. We're talking about topsides of maybe 5,000, 6,000, 7,000 tons, where now we're talking about topsides 70, 80, over 100,000 tons. So things have moved on a little bit. And since the late 1990s, our office and I have been involved in FLNG technologies of different sizes and applications. We've done all the way from small barges, self-propelled units, to the very largest units for Arctic environments, units for cyclonic environments. We were responsible for the concept design and basic design of Shell's G-Fling, that became Prelude. Worked on that between 2006 and 2009. And we cover the whole of the design of the barge and also offer, on top of that, the process engineering, not just the cargo systems that would go normally along with shipyard scope, but actually the topsides process as well. So we can offer the full design service of an FLNG, and this is what I want to try to go through now. Some of the design arguments that we'll we'll go through. Okay, so the key design drivers. The hull, or the substructure as it seems to be called now, is basically there to afford the topside somewhere to live. So the upper deck layout is absolutely paramount. And the drivers that drive that are the actual modules themselves, their footprint, the area of the modules, the layout of the modules, where they're located longitudinally, transversely, and also vertically. Separation. Now, these two items, whether it's an FLNG or an oil FPSO, are the same. We don't have the separation implications on oil FPSOs that we do on FLNGs. So providing that separation has an impact on the amount of footprint we have to provide, because we have to provide a hull form that not just supports the vessel but has kindly motions and allows the process, and more importantly, the people to operate safely and with minimum downtime. Another aspect that gets onto us is the height of the process deck above the main deck of the FPSO. Typically on an oil FPSO you might be talking 4.5 meters. Typically on an FLNG towards 8 or even more meters above the deck. That causes me a problem because basically I think of three things. I think of weight, I then think of weight again, and then I think, where is that weight? So you're pushing what is the vertical center of gravity of that, the top side, which is automatically, as I've just said, got heavier, higher up, which if you have anything in a bath, so put it too high, it turns over. That's a bad thing for naval architects to design. So the process deck elevation has an influence on my design. Craneage, maintenance weirs, workshops. Very important to work out how you're going to maintain this very large and complex plant, laydown areas. Main power generation. Some of the largest flings can certainly have in excess of 200 megawatts. So they're not unsubstantial power generation requirements. Cooling water. There's a vast amount of cooling water need for the liquefaction systems, and we've got to find somewhere, either just outside or within the hull, to provide that. Escape routes, very important, especially with an LNG train. The mooring option obviously drives where we have it. Do we have a turret? Can we go spread moored? The accommodation size. Some of these vessels have quite a large accommodation, up to 400 people. Do we put it at the fore end or do we put it at the aft end? And then finally, as we've discussed, as others have discussed, the offloading systems, whether we use a side-by-side, as has been done by Prelude, a tandem offloading system, either using a hard arm technology or flexible hoses, or could we go to a buoy in the future? So that drives the size of my ship in 2 dimensions for my hull form. Topside process, as I've said, weight. I'm a naval architect, like Archimedes. I've got to make it float. Buoyancy's got to balance out weight, and the center of gravity. I have to counter that to make sure that the vessel is stable and doesn't fall over. As I've said, the modules now for an FLNG facility typically are quite big, and I've got separation areas. So on an FLNG, quite typically now, I'm required to accommodate a lot of either such things as the prime movers, the e-build and switch and transformation, or cooling equipment, nitrogen generation equipment that topsides can't accommodate on the top side anymore within the hull. So all of a sudden that's become a little bit more difficult. Then, what containment system do we use? I'm not going to go into which containment system has its pros and cons. They all have certain pros, they all have certain cons. Another is, how do I fit my cargo? How do I do it to get a balance? Remember, a ship is like a seesaw. I've got to make it float level, not by the bow or by the stern. So where do I position my, where do I position my LNG, LPG and condensate? And do I put them all in a line? Do I try to wrap them around each other? I've got certain different options. I said a little bit of a mistruth earlier on. I don't just have to support the top sides. I have to provide storage for the product that we've produced, whether that be the LNG, LPG that's been liquefied or the associated condensate. So we'll have to know, typically, what production value the LNG train has and the well itself. What's the optimum loading, the offloading parcel size? What buffer storage do we need? And something that isn't always brought into play is the inspection philosophy for the tanks, whether that be the LNG, LPG, or condensate. I'm also affected by what regulations I've got to adhere to, and obviously the chemical requirements for either down well or the system itself, and obviously any refrigerants that are associated with the liquefaction process. Obviously, where the LNG facility is, it governs what my solution is going to be, whether it's near shore or offshore, benign or very harsh seas. Also, what the seas are like, whether they're just a simple system sea, have you then got long period swells together with wind-driven sea waves coming in at different directions, wind predominantly at another direction, that all comes into play, wind and current. What acceptability or what levels do I have to get for motions of that unit for personnel, but also process? Because that can affect the downtime and therefore the ability of the project to move forward from a technical and financial point of view. Obviously, the environment has a direct effect on the loads, on the mooring system, and any extreme loads on the hull. Then we do come to the mooring system itself. That drives the design. What water depth? Does it need a weather vane? Do I have to bring the ship back onto station to align it for offload, so it's aligned into the predominant swell, so we minimize roll for offloading? What number of type of risers obviously comes in? I'm not a mooring man. I'm not a turret designer, but all these come in to their scope and therefore my scope. So, regulatory framework, different to a ship. We do class the whole structure is classed with the classification society, but it's still covered by the safety case, and everything's to be made a LARP, along with the process and along with the mooring system. We must think, and this is most important, it is an asset itself. It isn't a hull with some topsides, with some mooring systems going down to a subsea. It is one cohesive solution to a problem. If we do that, we've got a good chance of getting a good solution. I do have to, however, comply with international maritime regulations, safety of life at sea, pollution, load line, collision regulations. Obviously, this vessel is flagged. It belongs to a country, so there are regulations that go along with that country, its maritime regulations. Obviously, it's going to be classified. Sometimes it can be classified by 2 classification societies, which makes life a little interesting. And until very recently, we didn't have any FLNG specific rules. We had some offshore rules, or we applied a mixture of the ship rules. That's becoming a little bit more clearer now. One set of standards that can cause some issues are company standards. I'm not saying company standards are bad because they're based on operational practice. However, if the fabricator and the shipyard don't understand those company standards and you just quote them in a spec, that could cause a price increase because they're going to put some margins in there to mitigate any risk because they don't know what the implications are going to be. So the company standards must be applied in a robust and rigorous manner and explained to the tenderers. And obviously the heli deck offloading Accommodation. Accommodation is a good one because that can drive. And we went to standard sort of International Labour Organization regulations. Massively different, say, to NORSOC. And then some company standards are way, way above that. There's certain facilities being constructed at the moment that have absolutely fantastic accommodation. So, naval architectural considerations. So firstly, the hull configuration. It is governed by the environment. If I'm somewhere benign, very sheltered, I can just go a square barge. If I'm somewhere extremely harsh, I have to have a ship-shaped form to be able to ride out the environment that's there. It actually drives that form. The accommodation location derives the hull configuration. If I've got an accommodation arrangement forward, and I'm in a harsh environment, and therefore I have to produce some shape at the fore end, I have to fit an accommodation block at the fore end. So that has some shaping to do. Where are my mooring systems? Where are my risers? Are we going to make it disconnectable? If I make it disconnectable, it's no good just disconnecting it. You have to let it run away. Therefore, it has to have propulsion. Therefore, it has to have an aft end that affords good propulsion characteristics, and you also want to then look at the resistance characteristics of the hull and maybe more shaping. And obviously, the offloading system comes into play if you've got a stern offloading system, for argument's sake. Probably the most important thing, especially for concept design, because once that happens, it's very hard to change it, are the principal particulars. Get the principal particulars wrong, that's the length, the breadth, the depth, the draft, that sort of thing. Wrong initially, you can do a lot of good work and you won't have a very good solution. So the derivation and the establishment of principal particulars that are appropriate to that vessel and its operation, whether that be its operation in a seaway or its operation as a production facility, are absolutely paramount. So they're driven, I'll not go through all of these, I've talked about a lot of them already, but you can see them, these drive the choice of principal particulars. I'll just dwell on one, that's the environment. I can tune the response of a hull depending on its principal particulars. I can change its natural periods for roll, to a lesser degree heave and pitch. So if I know good met-ocean data, I can make sure I detune it away from there rather than having to damp something that's already reacting to the seaway. Because you have to have the vessel's response characteristics aligned with the excitation forces, the sea, to get any motions. If you've got two separated, you don't get any responses and therefore any motions, and you've got a very good form. Regarding motions, we obviously look at the environmental data. It is, I know it's very difficult sometimes at early stages of design because maybe it's not available, to have very good met-ocean data, because that will drive these, as well as the weight of the topsides, the size of the topsides, what you're going to store inside the vessel, mooring, that sort of thing. I was alluded to before, we used to always look at operational 1 year, survival 100 year. Now we're looking at this absolutely extreme case, which is 10,000 year returns, and we're starting to sort of being forced to design towards them. So that's becoming more problematic. What we need to do is keep an eye on maximize personnel and process uptime, operability. The more time the system's available and the substructure allows the system to be available, the better. And we're going to perform downtime analyses to do this. We'd obviously perform sort of 2D strip theory, 3D panel theory analyses on it, maybe on double bodies with an LNG tanker coming alongside it. And it's not just on site. We've got to think about the tow, and the tow is just say a dead hull with no topsides if it's going to be integrated at a different facility to where the hull's built. And then the tow of the finished vessel to the site or to a dry dock. Because we have found in the past some designs are actually driven by the tow, and it's only towing for a couple of months of its life, and its life could be 25 to 30 years. You should not be designing a hull for a one-off event. You should be trying to design for this on-site system. And obviously we do that, we do all this sort of good stuff using some evaluation, but also now we've started using simulation. This is a bit like Groundhog Day. The first or the second talk on Monday showed this vessel work together with our friends at CB&I with Ron and SBM to produce this solution for a very harsh environment. So we've got the vessel in the simulator at South Shields College. That was an operational state. Now this is in its extreme state. This is in about 17 to 18 meter significant seas. And we're trying to design a hull for a vessel that will stay on station, that will be there for a safe, the production plant will be down, but it will be safe for crew to stay on. It may downman slightly, but it will not be totally abandoned and it will not sail away. And as you can see from here, the actual performance of this hull form's very good. We've done design features such as the boats being protected and all that. So a lot of thought went into this, even though it was just a concept. Okay. Obviously, I need to look at stability. Before how it moves is important, but the fact it stays upright is even more important. And when it's intact, but also under cases of damage. The survivability of the unit is absolutely paramount. We've got to look at what the extreme wave height data is to design the hull envelope, to design bulwarks, to take into account any immersions that we might get, bow waves, green seas on the vessel, but also emergencies. If we've got a very forward turret, the last thing I want to do is the bow to be coming out of the water, the turret spider to be exposed and to go down and cause significant damage. We can strengthen the steel in the hull to take that, but that's probably too much for the turret. We've got to look at wind loading. If we're in an Arctic environment, snow and ice. Cargo tank sloshing, and so in certain systems that's a problem. Also collision damages are to be looked at, especially if you're somewhere near a shipping lane. And also layout and operations, and I'll just hang on the idea of operations. A lot of the work that I could fix at a very early concept or basic stage of design, before you go into feed, if I can incorporate the operation of the vessel into there, I'll produce not just a technically very good design, I'll produce a very operationally optimum design. So we would look to try to look early days at things like temporary refuge or the escapes, the layout, the accommodation. Do you need bunker and handling stations? Marine engineers would look at the material handling studies, laydowns. How are we going to do crew transfer? Are we going to do it by helicopter? Are we going to do it by boat? Can we do it by helicopter? Because you're so far out. Cargo offloading as well. We don't often look at this, but again, going back to what Ron showed, we looked at this with the South Shields simulator to try to get the input of the operator. So here's the facility, the asset, in about a five-year environment. So it's a tandem offload in this one. So she's sitting there ready to take the LNG carrier. She's got thrusters on the aft end because she's got a turret about 15-20% aft. So we'll have to get the thrusters to bring her back. It's in a dual sea environment, so we're bringing her back to get head into swell to minimize the roll of the vessel. And once we've got her on station, we can then request that the LNG carrier comes on behind, ready to take the offload. And this sort of what I call simulation, not evaluation, is very, very important in that operations can get a good feeling for the design and offer their input into the design. And I'm a naval architect, and as Ron says, I can understand numbers. Other people that have lives and don't think about numbers all the time, this helps that for the communication of the design to other people. Okay, structural configurations. I've got a problem if I've got a Moss tanker. I think we can all accept that we're not going to build large FPSOs with Moss tanks. But if we did, this is what the whole structure would look like. Looking now at an SPB tank, I'm doing these in no particular order. That's traditionally what an SPB tank's probably going to look like, with a trunk deck. I really want a flat deck to land the topsides on. If I've got a trunk deck, I'm probably going to have to use a module support frame, which I'll come to in a minute, to support that. Also, this sort of thing, it's got a central spine going down the middle. These vessels are quite wide. And well, as I said before, we've got heavy, heavy units that are going to go there and there. So I can land, if I need to use stools, straight onto these main girders that are running there. And then the loads are passed straight down into the hull, and the support of the structure is very easy. However, there's no need really to have that from a sort of sloshing point of view. We can produce this sort of arrangement for an SPB tank, or, as I went to before, if we don't want to have it in series for the cargo, LNG, then LPG, then condensate, we could choose maybe to put condensate at the side. And that affords more protection from a collision from the side to produce a safer ship from a damage stability point of view. Same with the membrane, typical membrane, same as the ocean-going membrane tanker. Problem with this, you are going to get sloshing loads. You do have liquid restrictions, top and bottom, from about 90 to 10%, for argument's sake. You're going to have to tune the tanks, reduce the free surface. And that's why you see some of the configurations that are for membrane tanks with this central spine and a dual tank system. Obviously, the whole longitudinal strength of the vessel, these are big vessels. The largest one we've actually designed is 570 meters long by 85 meters wide, so they're actually very, very large vessels. So the longitudinal strength, and certainly deflections, we can mitigate the transmission of any of that to the topsides modules by using bridge bearings, etc. But still, the deflections in the hull are very important. And with any structure offshore, fatigue is. And certainly, if you are looking to a conversion, you'd have to think about that. We also want to know how we're going to support these. Typically, we use stools. And stools are okay. I prefer cruciforms, but a lot of people are going for pyramids. An MSF, a module support frame, which is standard shipbuilding practice, is the most kindly to the hull. It is most kindly for fatigue. But these are better for getting passage of air underneath so you don't get trapped gas. And obviously we've got to look at the integration of flares and that sort of thing, bulwarks, ice loads and blast loads. Marine systems, not too different to an FPSO really. Obviously your cargo systems are very specialised, and your process cooling water. Do you use sea boxes? Do you use caissons going down the side? Do you use caissons going down from within the hull, or do you use a moon pool reservoir? There's options there. And also, what type of offloading do you use? Electrical considerations. Again, some of these plants, as I said, can be in excess of 200 megawatts. And certainly ones that we've worked on we've used 33 kV, and one of them did use 66 kV because the power consumption was so great going to the main compressor motors. So in what sort of topsides power do you use? Steam? Probably nobody else will use steam. Gas turbine, dual fuel diesel. Where do you put your standby generators? Emergency generators, obviously you want that away from the process. And you'd have these sort of drivers for the loads. And if you're on an Arctic environment, trace heating is probably not insignificant. So, safety. These safety considerations are absolutely paramount, and we'd always look at all of these to try to make sure that we get as safe a design as we possibly can, taking all these into consideration. Other people have talked about these, so I don't think there's too much time. I'll just let you have a quick look at those. What we would always look at, though, from our point of view, is access and escape, the refuges, and how you evacuate. Primary evacuation being by a helicopter. Do you therefore need more than one helipad? And do you need refueling on that helipad because you're so remote from a heli base? And regarding the LSA on board, during campaign maintenance, you could have double or over double the operational crew. Do you keep all that LSA on board and have to keep it in class, or do you take it off and just fit it during campaign maintenance? I'll put this up because this is some work that we did about a decade or so ago into looking at how to exploit stranded gas reserves. These were oil reserves with associated gas, rather than a pure lean or a rich gas field. And there's a number of gas to pipeline. Well, that's a standard way of taking it. Gas to what we call transitory medium, LNG, but maybe there could be a point for CNG, to a liquid that's stable at standard temperatures and pressures. Fischer-Tropsch diesel, methanol, ammonia, or gas to wire. Certainly gas to wire near shore is a possible solution, and there's certainly a lot of people are building power barges now. And other things, obviously we've got FLNG developments possibly globally, but in a harsh environment, we maybe can't just take tank as a fortune. We've maybe got to build the whole transportation chain, and therefore we've got to look at designing and constructing DP shuttle tankers, both LNG and condensate, as you would for, say, operations in the North Sea. You'd have DP ones. And something else that we've been looking at, and a lot of people have, I know, is reusable facilities. So something like was mentioned, the Petroleum 1, I think, has been on about 6 or 8 platform fields in our life. A reusable multi-field development solution. I know that's easier for a oil platform than it is for an LNG because of the gas that's associated with it, making sure it's the same properties. But it is possibly something that we might have to look at or want to look at in the future. So, the conclusion, I would say, well, safety is paramount. It's my job to produce a safe operational platform for people and the process. But one thing, and other speakers have said this, so I'm just emphasizing it, that an integrated design team of process, marine, mooring, subsea, but also operations is absolutely key to the development of a good solution and all the way through feed to produce a good deliverable product. And as was mentioned by others, open communication. We're all batting for the same side. We're all playing together. And I know I work in a design office in essence, but to comprehensively explore the design space in a robust manner to make sure that nothing is going to come out and grab you further down the line, because to change lines and circles at a concept or basic design stage is not an expensive thing. Making sure your met ocean is accurate in the climate, whether you're working in hot, cold environments, whether you're going to stay on station or not. The integration structurally, especially when you've got high loads and very high topsides, redundancy of the system that you're going to have, what offloading you're going to do, the whole transportation methodology, and at day one try to bring in the maintenance and inspection strategy inherent within the design. So like I talked about detuning the design rather than trying to damp it for motions. Consider this at day one, and operationally it'll be far, far, far superior. Thank you very much for your time.
Thank you very much. Questions for Keith?
The Geordie accent, nobody understood it. English, but not like we know it.
No challenge, yeah.
I'm just wondering, how do you reduce sloshing in the SPB and membrane tanks?
It's basically, it's reducing the free surface and detuning the tank. So on a standard membrane tank, or some membrane ship, you've got quite large tanks. Let's say something in the region of 40, 50, 60,000 cubic meters. Those tanks have filling levels, or restricted filling levels because of sloshing loads. So you've got partially filled tanks. It happens on tankers as well, don't get us wrong, we'll have to look at that. But by detuning the tank and reducing the size of the tank, you therefore take its natural period away, and therefore by doing that you mitigate the effect of the motions on the tank and therefore the sloshing loads on the membrane. With the SPB tanks, there is no sloshing problems. The same with Moss tanks. The structural tanks, they'll take the load. So it's only in the membrane systems where they're very thin, the primary and secondary barrier, only less than a millimeter thick of invar, or whatever they are. So they're quite delicate, the baffles and that sort of thing.
Thank you.
Yes, you mentioned significant wave height of 17 meters.
Yeah.
Could you tell me which
No.
areas you're thinking about?
Northwest Australia.
No,
that's the
because
best I can
it's to me that smells Barents Sea, North Sea at its worst, and offshore Alaska. And is it likely that they would do offshore loading of LNG in those areas? Wouldn't a pipeline be more likely? So you would.
We've looked at 4, I can think of, LNG proposals for the Arctic. But what I showed there was not for the Arctic.
No.
It was.
So isn't that a little overkill?
No, that's what the Met Ocean says.
Yeah, but that was for Prelude, or was it for?
No, it's
No?
a different field. I can't tell you which one. I'm sorry. I hope you appreciate it. No. That is absolute extreme. So that's, do you choose to stay on board?
Yeah. My
this
point
guy?
is that I would believe in such areas you would it's you would know in such areas you would have access to pipelines most likely.
No. It's a facility, a floating facility that will stay on station, will not disconnect and move away, and will not demand, apart from maybe non-essential personnel, if they know that an event is coming. And that's a 10,000-year sea state.
Okay. Yeah.
I wouldn't like to be on board myself. Like. But it actually, one thing to point out is that the normal operating criteria that would use for standard trading tankers, which are sort of unrestricted worldwide service, the motions of that vessel were actually better than that. They never went beyond what would have for normal seafarers.
Yeah, question on the 10,000-year case. Is that a statistical projection from 10 years of Met-Ocean data, or is it a genuine assessment of what you might be faced in that period?
Well, there's statistics, and then Met-Ocean data. To be honest with you, I can't remember what the time series was that got that, but I couldn't talk about its validity. Afterwards, I'll talk about its validity, but I don't think I can say that in public. But yeah, it's an extreme event.